There is an ocean beneath the ice, not a lake, not a pocket of brine trapped in rock. An ocean, deeper than any ocean on Earth, with twice the total volume of every ocean on this planet combined, sitting beneath a shell of ice 50 kilometers thick, in complete, permanent, unbroken darkness. 485 million miles from the sun. And it has been there for 4 billion years. We have never seen it. No instrument has ever touched it. No light has ever reached it from above because the ice is too thick and the sun is too far. The ocean exists the way a fact exists that nobody has verified yet. Present, waiting, patient, indifferent to whether we know about it or not. What we have done is infer it, from the way Europa's surface cracks and reforms like a living skin, from the faint magnetic field fluctuations that only make sense if something electrically conductive is shifting in the interior, from the tidal stresses that Jupiter's gravity applies to the Moon every 85 hours, flexing it the way you might flex a foam ball, generating heat, and from that heat, keeping water liquid in a place where nothing should be liquid. The ocean is there. The question that has been building in planetary science for 30 years. The question that is behind every Europa mission proposal, every paper, every press conference, is what else is there? Because here is the thing about Europa's ocean that makes it different from every other speculative location for life in the solar system. It is not just liquid water. It has an energy source. It has chemistry. It has been operating continuously for a period of time longer than complex life has existed on Earth. It sits beneath a surface that is bombarded by Jupiter's radiation, radiation that breaks apart surface water molecules and creates oxygen, which cycles down through the ice, potentially reaching the ocean below. Europa's ocean may have exactly what life needs to start, and it may have had it for 4 billion years. The journey to find out is what we're doing tonight. Not in the abstract, not as a thought experiment, as a specific physical engineering reality, because we are actually going. NASA's Europa Clipper mission reached Jupiter's system in 2030. A lander is in development. The decision has been made at the level of real institutions spending real money that we are going to Europa and that we are going to find out what is in that ocean. And the journey, the actual physics of getting there, the radiation environment that makes Europa one of the most hostile locations in the solar system, the engineering of surviving long enough to ask the question, and the weight of what the answer might mean. That journey is what tonight is about. Before we begin, subscribe to Calm Theory for Sleep if you found us tonight. Like the video, and tell us in the comments where on this planet you're listening from right now. We want to know. The geography of who's out here thinking about this with us matters. Now, let's go to Europa. Jupiter has 95 known moons. Most of them are small, irregular, captured objects. Rocky debris that wandered too close to Jupiter's gravity and never escaped. 4 of them are not. Io, Europa, Ganymede, and Callisto were discovered by Galileo Galilei in January 1610. The first objects confirmed to orbit something other than Earth. For the first time in human history, there was proof that not everything in the sky moved around us. Galileo called them the Medicean stars, after his patrons. History calls them the Galilean moons. They are, by any measure, worlds. Not rocks, not debris, but substantial objects with complex geology, and, in at least one case, the conditions for life. Europa is the smallest of the 4 Galilean moons and the 6th largest moon in the solar system. Its diameter is 3,121 kilometers. slightly smaller than Earth's moon. It orbits Jupiter at an average distance of 671,000 kilometers, completing one orbit every 85 hours and 13 minutes. That orbital period is precisely synchronized with Ios and Ganymedes in a gravitational resonance. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This resonance is not a coincidence. It is maintained by the gravitational forces between the 3 moons, which lock them into specific ratios and continuously pump energy into their orbits. The consequence for Europa specifically is that its orbit is kept slightly elliptical rather than perfectly circular. And a slightly elliptical orbit means that Europa's distance from Jupiter varies slightly throughout each orbit, which means Jupiter's gravitational pull on it varies, which means the moon is continuously flexed, compressed, and stretched by the varying tidal force. That flexing generates heat in the interior. The same principle as bending a metal rod back and forth. The metal heats up at the point of bending. Europa's interior heats up from tidal flexing, and that heat is enough, in combination with the initial heat from formation and the ongoing radioactive decay in the rocky core, to maintain a liquid water ocean. The ocean is believed to sit between the ice shell above and the rocky mantle below. The ice shell is estimated at 15 to 25 kilometers thick in some estimates, up to 50 kilometers in others. The uncertainty reflects the limits of what we can determine from remote observation. Beneath the ice, the ocean extends to depths of perhaps 100 kilometers. The total water volume is approximately 3 times the total volume of Earth's oceans. The floor of Europa's ocean, where water meets rock, is where the most interesting chemistry may be happening. On Earth, the boundary between ocean water and the basaltic rock of the seafloor is one of the most chemically active zones on the planet. Hydrothermal vent systems push hot mineral-laden water up through the seafloor, creating gradients of temperature, chemistry, and pH that support rich ecosystems entirely independent of sunlight. The organisms at hydrothermal vents run on chemical energy, using the reaction between the mineral-rich vent fluid and the surrounding cold seawater as their energy source. The same way a battery uses a chemical reaction between its electrodes. These ecosystems were discovered in 1977. Before that discovery, life was understood to require sunlight. After it, the definition of what life needs was fundamentally revised. You do not need sunlight. You need liquid water and a chemical energy source. And Europa has both. The chemistry in Europa's case involves the tidal flexing interacting with the seafloor to drive water through the rock, a process called serpentinization, in which water reacts with iron and magnesium-rich minerals to produce hydrogen gas and heat. Hydrogen is an energy source. Organisms that can oxidize hydrogen, combining it with available oxidants like sulfate or carbon dioxide, can extract energy from this reaction and use it for growth and metabolism. And where do the oxidants come from in an ocean sealed beneath 50 kilometers of ice with no contact with the atmosphere? From above, from the ice surface, from the radiation. This is where Europa's story turns from promising to terrifying, and why the journey to Europa is categorically different from the journey to any other destination in the solar system. Jupiter has the most powerful magnetic field of any planet in the solar system. It is roughly 20,000 times stronger than Earth's magnetic field at the planet's surface. And it extends enormous distances into space. Jupiter's magnetosphere is so vast that if it were visible, it would appear larger than the full moon in Earth's night sky. Within this magnetic field, charged particles, electrons and ions, are trapped and accelerated to extreme velocities. Europa orbits inside this radiation field. The specific environment around Europa is one of the most radiation-intense locations in the solar system, accessible to a spacecraft. The radiation dose at Europa's orbit is approximately 5,400 rem per day. To put this in human terms, a whole-body radiation dose of 500 rem in a single day is lethal without immediate medical treatment. Astronauts on the International Space Station receive roughly 0.5 rem per day, already elevated above Earth's surface level. At Europa, the dose rate is 10,000 times the ISS level. An unprotected human at Europa's orbital distance would receive a lethal radiation dose in approximately 2 hours. This is not incidental background radiation. This is a continuous bombardment of high-energy electrons and ions moving at significant fractions of the speed of light, penetrating materials, ionizing atoms, breaking molecular bonds, destroying electronic circuits, and damaging biological tissue at a rate that makes survival without substantial shielding a short-term proposition. The radiation is not uniform in direction or energy. It comes in particle species, ranging from electrons at millions of electron volts to sulfur and oxygen ions at billions of electron volts, arriving from all angles as the rotating magnetic field sweeps around Jupiter once every 10 hours. Shielding against the most energetic particles is extraordinarily difficult because high-energy particles penetrate materials more deeply than lower-energy ones. Standard radiation shielding strategies, using dense materials to stop particles, work against X-rays and lower-energy ions, but are less effective against the ultra-high energy electrons and ions present in Jupiter's radiation belts. Making things more complicated, when high-energy particles strike shielding material, they produce secondary radiation, a cascade of lower-energy particles produced when the primary particle interacts with the atomic nuclei and electrons of the shielding. This secondary radiation itself irradiates whatever is behind the shield. The shielding is not a perfect solution. It is a trade-off between the primary radiation exposure and the secondary radiation produced. For spacecraft electronics, the radiation causes a specific category of damage called total ionizing dose damage. Over time, the accumulated charge deposited in semiconductor materials changes their electrical properties, eventually causing circuits to fail. Spacecraft visiting Jupiter's inner moons have historically used radiation-hardened electronics, components specifically designed to tolerate higher accumulated doses before failing. And even these have limits. Europa Clipper, NASA's flagship mission to the Jupiter system that launched in October 2024 and arrived at Jupiter in 2000, addresses the radiation problem through a specific mission architecture. Rather than orbiting Europa directly, the spacecraft orbits Jupiter and makes multiple flyby passes of Europa, spending minimal time in the worst of the radiation environment while accumulating science data over dozens of close approaches. The total accumulated dose over the mission's projected 45 flybys is estimated at approximately 2.9 million rad, within the designed tolerance of the radiation-hardened electronics, but right at the edge of what the spacecraft can survive. This is the radiation environment that any mission to Europa must navigate. It is not an obstacle that better technology will eliminate. It is a fundamental feature of the physical environment, set by Jupiter's mass and magnetic field, unchangeable by any human engineering. For a crewed mission, for any scenario in which human beings travel to Europa, the radiation problem becomes the central design constraint around which every other engineering decision must be made. Before we confront what it would mean for humans to be at Europa, let's talk about what it takes to get there at all. Jupiter is the largest planet in the solar system, with a mass 318 times Earth's, orbiting the Sun at an average distance of 5.2 astronomical units, 5.2 times the Earth-Sun distance, or roughly 778 million kilometers. Europa, orbiting Jupiter, is roughly 630 to 930 million kilometers from Earth, depending on where both planets are in their respective orbits around the Sun. At the closest approach, Jupiter is about 588 million kilometers from Earth. At this distance, light takes approximately 33 minutes to travel from Earth to Jupiter. This is the communication delay. Any signal sent from Earth to a spacecraft at Jupiter takes 33 minutes in the best case and up to 52 minutes in the worst case to arrive. Instructions sent from Earth arrive at Jupiter before the next orbit, not within seconds. Getting a spacecraft to Jupiter in a reasonable time requires a trajectory that uses planetary gravity assists. Swing-by maneuvers in which the spacecraft approaches a planet closely enough to steal a small amount of that planet's orbital momentum, using the gravitational interaction to redirect and accelerate the spacecraft without burning propellant. The specific trajectory design determines the travel time and the energy budget. Europa Clipper launched in October 2024 and used a Mars gravity assist in March 2025, followed by an Earth gravity assist in December 2025, before finally arriving at Jupiter in April 2030, a total journey of approximately 5.5 years. This trajectory was chosen to balance travel time against launch vehicle capability and fuel budget. A more direct trajectory would have been faster, but would have required a much more powerful launch vehicle. For a hypothetical crewed mission to Europa, which no space agency is currently planning but which serious engineering studies have examined, the travel time problem becomes a central challenge. The minimum travel time from Earth to Jupiter, using a Hohmann transfer orbit, is approximately 2 years and 9 months each way. This is the most fuel-efficient trajectory, but also the slowest. Higher energy trajectories can reduce travel time, but require dramatically more propellant. And propellant is mass, and mass is the fundamental currency of spaceflight. Every kilogram of propellant you want to carry to Jupiter requires additional propellant to launch it from Earth, which requires additional propellant to launch that propellant. In the exponentially compounding relationship known as the Tsiolkovsky rocket equation, practical crewed Jupiter missions, using propulsion technologies that are either currently available or likely to be available within the next few decades, would take between 2 and 5 years of travel time each way. A round trip, even without surface operations, would span 5 to 10 years. For comparison, the Apollo missions to the Moon took 3 days each way. The longest human spaceflight on record, as of the mid-2020s, is approximately 1 year, conducted aboard the International Space Station. No human has ever traveled more than roughly 500,000 kilometers from Earth. Jupiter is more than 1,000 times farther than the Moon. The human body was not designed for this. The problems that long-duration spaceflight poses to human physiology are well documented from the data accumulated during ISS missions, and they are severe in ways that compound over time. Bone density loss occurs in microgravity at a rate of approximately 1 to 2% per month in the load-bearing bones of the spine, hips, and legs. On Earth, the mechanical stress of standing and walking continuously stimulates bone remodeling. Osteoblasts deposit new bone tissue, while osteoclasts remove old bone, maintaining density. In microgravity, the loading stimulus is removed. The removal process continues, but the deposition process slows. Astronauts returning from 6-month ISS missions have bone density equivalent to someone 30 years older. After a 5-year journey to Jupiter, even with aggressive exercise countermeasures, the structural integrity of the crew's bones would be significantly compromised. Muscle atrophy parallels bone loss. The muscles of the lower body, which exist primarily to hold us upright against gravity, lose mass rapidly without the constant loading that walking and standing provide. After long-duration spaceflight, astronauts require physical rehabilitation for weeks or months before they can walk normally. For a crew arriving at Jupiter after years of microgravity, the ability to perform any physical work immediately upon arrival would be severely limited. Fluid shifts in the body occur immediately upon entering microgravity. Without gravity pulling fluids downward, the fluid distribution in the body equilibrates more evenly. Blood and interstitial fluid shift toward the head and chest, away from the legs. This causes facial puffiness and nasal congestion, both temporary. More seriously, the fluid shift in the head increases the pressure in the skull, intracranial pressure, which flattens the back of the eyeball and causes swelling of the optic disc. In a significant fraction of long-duration astronauts, this produces measurable permanent vision degradation. The mechanism is not fully understood, and no reliable countermeasure currently exists. The immune system is suppressed in long-duration spaceflight. The specific mechanisms are complex and involve multiple pathways, but the clinical consequence is an elevated susceptibility to infection and an increased reactivation of latent viruses, including herpes viruses like Epstein-Barr and varicella zoster that exist in the human body permanently after childhood infection. Under normal circumstances, the immune system keeps these viruses suppressed. In the immunosuppressed environment of prolonged spaceflight, they can reactivate. Astronauts on the ISS show elevated rates of viral reactivation, though typically without severe clinical consequences during short missions. Over years-long missions, the cumulative effects of immune suppression are a real health threat. And then there is radiation. Even without the specific enhancement of Jupiter's radiation belts, interplanetary space is a radiation environment far more intense than Earth's surface. The galactic cosmic ray background, high-energy particles arriving from outside the solar system, and the intermittent solar energetic particle events produced by solar flares and coronal mass ejections combine to expose deep space travelers to radiation doses many times higher than Earth's surface. Residence. Current estimates suggest that a round-trip Mars mission, considerably shorter than a Europa mission, would expose astronauts to a radiation dose approaching or exceeding the lifetime career limits established for astronauts by NASA and other space agencies. A Europa mission, longer and ending at the most radiation-intense environment in the solar system, would far exceed these limits. These are the baseline problems, the problems that exist on the way to Jupiter, before the ship gets anywhere near Europa's radiation belts. Arriving at Jupiter requires slowing down. A spacecraft traveling from Earth to Jupiter on a standard trajectory arrives moving too fast to be captured by Jupiter's gravity. Without decelerating, the spacecraft would swing around Jupiter in a hyperbolic trajectory and continue outward into deep space. To enter orbit around Jupiter, the spacecraft must fire its engines against its direction of travel, a retrograde burn, to reduce velocity enough that Jupiter's gravity can capture it. The amount of velocity change required, the delta V in the vocabulary of orbital mechanics, is enormous. For Europa Clipper, the Jupiter orbit insertion burn lasted approximately 35 minutes and required the spacecraft's main engine to operate at full thrust for that entire duration, consuming a substantial fraction of the mission's total propellant budget. For a crewed ship, which would be far more massive than any robotic spacecraft, the propellant requirement for Jupiter orbit insertion would be proportionally enormous. The Tsiolkovsky rocket equation dictates that the amount of propellant required scales exponentially with the desired velocity change, not linearly. Doubling the mass of the spacecraft more than doubles the required propellant mass, because you need additional propellant to accelerate the propellant itself. This is the fundamental engineering constraint that makes crewed outer planet missions so difficult. The farther and faster you want to go, the more propellant you need. The more propellant you carry, the more propellant you need to carry that propellant. The equation has no favorable solution for chemical propulsion at Jupiter distances. Nuclear propulsion, whether thermal or electric, offers substantially better efficiency and is the technology that most serious mission architecture studies identify as the minimum viable option for crewed Jupiter missions. Nuclear thermal propulsion heats a propellant, typically liquid hydrogen, using a nuclear reactor, producing exhaust velocities roughly twice those achievable with chemical rockets. A nuclear thermal engine can do the same job as a chemical engine, with less than half the propellant. This does not make the Jupiter mission easy. It makes it less impossible. Nuclear electric propulsion takes a different approach. The reactor produces electricity, which powers ion thrusters that accelerate propellant to much higher velocities than nuclear thermal, with proportionally lower thrust. Ion drives produce very little thrust, but extremely high efficiency. They can continue thrusting for months or years, gradually building velocity without the massive propellant requirement of a high-thrust burn. The trade-off is time. Low-thrust trajectories to Jupiter take longer than high-thrust trajectories, but require far less propellant. For a crewed Europa mission, the architecture that most studies favor involves nuclear electric propulsion for the transit phase, combined with chemical or nuclear thermal propulsion for the orbital insertion maneuvers at Jupiter. This is a technically demanding combination that requires systems beyond the current state of the art, but not beyond the foreseeable future of space engineering. The specific challenge of Europa, compared to other potential targets in the Jupiter system, relates to its orbital position inside the radiation belts. Getting to Europa is not just getting to Jupiter. It requires navigating from whatever orbit the spacecraft enters at Jupiter through the radiation environment to Europa's orbit. Every day spent in the inner part of the Jovian system accumulates radiation dose. Mission planners for crewed Europa missions would need to carefully design the trajectory to minimize radiation exposure during transit to and from Europa, potentially spending weeks or months in a shielded parking orbit at a distance far enough from Jupiter to reduce the radiation dose rate to manageable levels before making the closer approach. Let's step back from the engineering for a moment and think about the place itself, because it matters for understanding what a mission there would actually be trying to do. Europa's surface is ice, not ice like the ice in a freezer. Ice that has been processed by billions of years of tidal flexing, cracking, refreezing, and exposure to Jupiter's radiation environment. Ice that is brown and reddish in places where organic compounds produced by radiation chemistry have accumulated in the cracks. Ice crossed by tens of thousands of kilometers of fracture systems, some of them global in extent, some of them refilled and refrozen so many times that they show multiple generations of activity layered on each other. The surface is young, by planetary standards, geologically recent. Some estimates put the average surface age at only 20 to 100 million years. This is remarkable. Earth's ocean floors, which are among Earth's youngest surfaces, are up to 200 million years old. Europa's entire surface may be younger than the last major dinosaur diversity. The youth of the surface implies that it is continuously being resurfaced. Old ice is being destroyed and new ice is being created, which requires that the ice shell is actively moving and that material from beneath is reaching the surface. The specific mechanisms of resurfacing are debated. One mechanism is true polar wander, the slow reorientation of the entire ice shell relative to the interior due to changes in the distribution of mass. Another is convective overturn within the ice shell. Warm ice from the bottom of the shell rising as plumes and cold ice from the surface sinking. A third is cryovolcanism, the eruption of liquid water or water ice slurry from the interior through fractures to the surface. The third mechanism, cryovolcanism, has received intense attention because it would mean that Europa's ocean is periodically in direct contact with the surface. Plumes of water vapor and possibly liquid water ejected from the surface would carry ocean material into space, where it could be sampled by a passing spacecraft without requiring a landing or drilling through 50 kilometers of ice. In 2012, the Hubble Space Telescope detected what appeared to be water vapor plumes above Europa's south polar region. The observations were tantalizing but not definitive. The signals were at the edge of what Hubble could detect, and subsequent observations did not consistently reproduce them. In 2016, more Hubble observations produced additional candidate plumes. Europa Clipper's observations during its flyby campaign are designed specifically to characterize whether the plumes are real, and, if so, to sample their composition. If the plumes are real, and the evidence is suggestive if not conclusive, they represent one of the most scientifically valuable opportunities in planetary science. A spacecraft flying through a plume could, in principle, sample ocean water that has been carried directly from the interior to space, analyzing its chemistry without ever landing on the surface or drilling through the ice. The presence of amino acids, complex organic molecules, or other biosignatures in the plume material would be extraordinary evidence for life in the ocean below. The surface textures of Europa tell additional stories. There are regions called chaos terrain, areas where the surface appears to have melted, or nearly melted, broken into fragments that have rafted around on a liquid or semi-liquid substrate and refrozen in new positions. These regions look, in satellite images, remarkably like the pack ice of the Arctic Ocean, as seen from above, a jumble of fragments separated by refrozen water. They imply that at some point in the recent geological past, the ice shell in those areas was thin enough to allow significant disruption from below. There are also regions of smoother terrain, younger in appearance, that may represent areas where the surface has been recently resurfaced by material from below. Long linear ridges, some extending for thousands of kilometers, formed where fractures opened and water or ice slurry was pushed up from below, freezing on contact with the cold surface. The surface, in total, is a record of billions of years of interaction between the ice shell above and the ocean below. Reading that record, understanding what it reveals about the ice shell thickness, the ocean composition, the geological history, is one of the central scientific goals of Europa Clipper and any subsequent lander mission. If the scientific goal is to determine whether life exists in Europa's ocean, a flyby spacecraft, even one as sophisticated as Europa Clipper, can only get part of the way there. The definitive answer requires reaching the ocean. And reaching the ocean requires either sampling plume material that comes from the ocean, which depends on the plumes being real and accessible, or landing on the surface and drilling through the ice. Both approaches face engineering challenges that are severe enough that neither has been fully solved. Landing on Europa is not like landing on Mars or the Moon. The surface is not flat, sandy plains or gentle cratered terrain. It is a complex landscape of ridges, pits, and chaos regions, with slopes and crevasses and fragile ice formations that could collapse under a lander's weight. The surface composition varies. Some areas are relatively pure ice. Others are contaminated with salts and organic compounds that change the mechanical properties. The radiation environment means that any surface operations must be completed as quickly as possible, because every minute on the surface accumulates radiation dose that damages the lander's electronics. There is also the question of what the surface is actually like at the scale of landing. Europa's surface has been imaged by the Voyager probes in the 1970s, and by Galileo in the 1990s, and by Earth-based telescopes. But the highest resolution images available, as of the mid-2020s, show features no smaller than about 250 meters. A lander descending to the surface needs to navigate features at the meter scale. Boulders, ridges, depressions that could trap or tip the lander. Europa Clipper's highest resolution imaging campaign will provide the data needed to select landing sites for a future lander. But the landing itself remains an extraordinarily challenging operation. Drilling through the ice is a separate and even more formidable challenge. 50 kilometers of ice, at temperatures from -170 degrees Celsius at the surface to near the melting point at the base of the ice shell. Drilling through rock is challenging but well understood. Drilling through ice at these depths is a different problem. The drill must generate heat to penetrate the ice, but that heat causes the ice to melt and refreeze around the drill, potentially trapping it. The drill must prevent the borehole from collapsing while it descends. It must operate autonomously, because the communication delay between Earth and Europa makes real-time control impossible. And it must eventually transmit data from the ocean floor back to the surface, through 50 kilometers of ice, or through the borehole. The communication problem alone is significant. Electromagnetic signals do not propagate efficiently through ice. Getting data from a probe in the ocean up through the ice shell to a lander on the surface, which can then transmit to an orbiter, which can then transmit to Earth, requires either physical wire connections running through the borehole or acoustic communication through the ice, or some other mechanism. Each approach has limitations. The specific design of what is sometimes called a cryobot, a probe that melts or drills its way through ice to reach a liquid water layer beneath, has been studied for decades. Concepts range from simple heated probes that melt straight down through the ice, to more complex designs that carry communication tethers, or deploy autonomous underwater vehicles to explore the ocean once they reach it. NASA's development of a Europa lander concept, ongoing since the late 2010s, envisions a system that would land on the surface, sample the top centimeters of ice and any surface material, and analyze it for biosignatures. This is a much more limited goal than reaching the ocean itself. It is sampling the surface rather than the interior. But it is an achievable step that could provide critical information about what the ice shell contains and whether material from the ocean reaches the surface. The ambitious long-term goal, a probe in Europa's ocean, is what the scientific community wants. The engineering to make it happen is not yet ready, but the pieces are being assembled. If there is life in Europa's ocean, It has been evolving in complete isolation for 4 billion years. Not in isolation from the physical environment, the tidal flexing, the hydrothermal chemistry, the slow delivery of oxidants from the surface, but in isolation from any other biosphere, from any evolutionary competition with Earth life, from any of the contingent events that shaped the specific forms of life on our planet. It would be truly alien. Not alien in the science fiction sense of green skin and different anatomy. Alien in the biochemical sense. Its proteins might be made from different amino acids than Earth life. Its genetic information might be stored in different molecules. Its membrane chemistry might be different. Its metabolic pathways might exploit chemical gradients that have no analog in Earth's biosphere. Or it might not be. The chemistry of carbon in water, under reducing conditions, follows specific thermodynamic pathways that may constrain the forms that life can take more than we realize. The building blocks of life, amino acids, nucleotides, lipids, are produced by chemistry that operates under the physical laws of the universe, and those laws are the same everywhere. It is possible that life in Europa's ocean, given enough time, would converge on similar biochemical solutions to the same fundamental problems. The question of what biosignature to look for is therefore not trivial. The most unambiguous biosignature would be a living organism, a cell, or something morphologically recognizable as a self-replicating entity. Next would be complex organic molecules in patterns too specific to have arisen by abiotic chemistry. Then, isotopic signatures. The specific ratios of carbon-12 to carbon-13 or sulfur-32 to sulfur-34 that biological processes produce through their selective use of lighter isotopes. Then indirect chemical evidence, specific mixtures of compounds that could not coexist in equilibrium without a process continuously generating one of them, which is the kind of disequilibrium that life produces by driving chemical reactions away from equilibrium. Each of these biosignatures requires different detection capabilities and different levels of contact with the ocean. The most direct biosignatures, living cells or recognizable organisms, require reaching the ocean. Isotopic signatures and chemical disequilibrium signatures might be detectable in plume material or in surface ice that has been contaminated with ocean material through the cryovolcanic processes. The instruments on Europa Clipper, particularly MASSPEX, the mass spectrometer designed to characterize plume material chemistry, and ETEMIS, the thermal imager, are designed to detect some of these biosignatures if the plumes are active and accessible. The surface composition instruments, MES and UVS, characterize the chemistry of surface materials that may include ocean-derived compounds. What the mission cannot do, definitively, is confirm the presence of life. The instrumental sensitivity and the nature of what the mission can access, surface material and plume composition, limit the strength of any positive result. Europa Clipper is designed to characterize the habitability of Europa's ocean and look for the most detectable evidence of life or its chemical precursors. It is not designed to be the mission that discovers life. That mission, the one that provides a definitive answer, requires either a lander with surface drilling capability or a cryobot probe that reaches the ocean. It is the mission that planetary scientists have been building toward for 3 decades. It is the reason every Europa mission precedes it. It is, in the vocabulary of NASA mission planning, the next logical step. If Europa's ocean is sterile, if the chemical analysis of plume material and surface ice and eventually ocean water shows complex organic chemistry, but no life, no biosignatures, No evidence that the 4 billion years of continuous habitability produced anything living. That is itself a profoundly important result. It would tell us that habitability is necessary but not sufficient for life, that liquid water and energy and chemistry are not enough, that something else is required, something we have not identified, something more specific or more improbable than the general conditions Europa provides. If the ocean is sterile, the number of potentially inhabited worlds in the universe contracts. Every place we thought was promising becomes less promising. The probability that life arises whenever conditions allow it becomes lower. We become, potentially, lonelier. If Europa's ocean contains life, even the simplest microbial life, even a single type of organism using a single metabolic pathway, the implications cascade in the opposite direction. The probability that life arises wherever conditions allow immediately skyrockets. The number of inhabited worlds in the galaxy goes from a guess constrained by 1 data point to a guess constrained by 2, and 2 data points in the same galaxy, in the same solar system, indicate that life is not a miracle, but a consequence. Not a singular event in cosmic history, but a recurring one. 2 inhabited worlds in one solar system means that every solar system is likely to harbor life. 200 billion solar systems in the Milky Way, 2 trillion galaxies in the observable universe. If life arises wherever conditions allow, and 2 worlds in our solar system have those conditions, then the universe is full of life in a way that redefines what the universe is. The discovery of life in Europa's ocean would be the most significant finding in the history of science. More significant than the Copernican revolution, which removed Earth from the center of the solar system. More significant than Darwin's discovery of natural selection, which removed humans from a special place in biology. More significant than the discovery of the Big Bang, which placed our universe in a history rather than outside it. It would be the discovery that life is a property of the universe, not an exception within it. We are going to Europa to find out. The journey is already underway. Before Europa Clipper, before any of the missions currently being planned, one spacecraft gave us most of what we know about Europa's interior. The Galileo spacecraft launched in October 1989 and arrived at Jupiter in December 1995, beginning a mission that would last until 2003. It was not designed primarily to study Europa. Its mission was the entire Jovian system, including all 4 Galilean moons, Jupiter's atmosphere, and the magnetospheric environment. Europa was one of many targets, and yet the data Galileo collected from Europa transformed our understanding of that moon more completely than any previous observation. Galileo made 11 close flybys of Europa during its primary and extended missions, passing within 200 kilometers of the surface on its closest approach. From those flybys, it gathered the data that made the subsurface ocean hypothesis go from speculation to the working hypothesis of the planetary science community. The magnetic field measurements were key. Galileo carried a magnetometer, and during its flybys, it detected a distinctive signature in Europa's magnetic environment. Jupiter's powerful magnetic field sweeps past Europa every 10 hours as Jupiter rotates. In a body with no internal magnetic field of its own, this changing external field induces electrical currents in any electrically conducting material within the body. The same principle as induction in a transformer. Those induced currents generate their own secondary magnetic field that Galileo could detect. The strength and character of Europa's induced magnetic field, measured across multiple flybys at different phases of Jupiter's rotation, was consistent with a global layer of electrically conductive material at shallow depth, specifically with a salty liquid water ocean. The salinity of the water matters. Pure water is not a good conductor. But water with dissolved salts, the same salts that make Earth's ocean electrically conductive, would produce exactly the induction signature Galileo measured. The alternative explanations, a conducting layer of ice containing salty pockets, or some unusual mineral layer, could not reproduce the measurements as well as the global ocean model. The inference was not airtight, but it was compelling. No subsequent analysis of Galileo's magnetometer data has found a more satisfactory explanation. Galileo's camera data provided the visual evidence that complemented the magnetic signature. The chaos terrain, the ridges, the young surface age, the apparent lack of large craters despite Europa's position in the inner Jupiter system, where impact rates are significant. All of these told a story of a geologically active surface being continuously renewed by processes from below. A frozen, geologically inert moon would accumulate craters over time without erasing them. Europa's crater-poor surfacing. Galileo's imaging resolution was limited by the spacecraft's damaged tape recorder, which forced the mission engineers to compress data heavily and discard some observations. Even so, the images revealed enough surface texture to establish the basic categories of Europa's terrain that subsequent missions have built on. The specific limitation of Galileo's data for the ocean hypothesis is that it could not see below the surface. The inference of an ocean is exactly that, an inference built on the convergence of multiple independent lines of evidence. Europa Clipper is designed to both strengthen that inference and begin characterizing the ocean's properties. Its depth, its salinity, the thickness of the ice shell, through more sophisticated measurements using technologies not available to Galileo. The Europa Ocean hypothesis has had 30 years to be challenged and has not been overturned. Every new piece of data has been consistent with it. At this point in the scientific process, the ocean is treated as a working reality, not a speculation. The questions being asked are no longer, is there an ocean, but what is in the ocean and how can we access it? Let's be specific about the tidal heating mechanism, because it is the physical engine behind everything that makes Europa potentially habitable. And understanding it changes how you think about the entire outer solar system. The gravitational force between two objects is not uniform across their extent. The near side of an object is pulled more strongly toward the source of gravity than the far side. This difference in force, the tidal force, acts to stretch the object along the axis pointing toward the gravitational source and compress it along the perpendicular axis. Earth's ocean tides are the most familiar consequence. The water on the side facing the moon is pulled more strongly than the water on the far side, creating two tidal bulges and the twice-daily rising and falling of the ocean level as Earth rotates beneath them. For a solid body, tidal forces cause elastic deformation. The body is stretched and compressed like a rubber ball being squeezed. If the orbital motion of the body causes the direction of the tidal force to change over time, the deformation continuously changes, and the elastic material must continuously flex. Whenever a solid material is deformed and then released, not all the deformation energy is returned as elastic energy. Some is lost as heat. The same way, a repeatedly bent metal rod heats up at the flex point. Europa's tidal heating comes from the fact that its orbit is elliptical. Because of the orbital resonance with Io and Ganymede, Europa's orbital eccentricity, the degree to which its orbit deviates from circular, is maintained at approximately 0.009, a small but non-zero value. A perfectly circular orbit would result in a constant distance from Jupiter, and therefore a constant tidal force. The elliptical orbit means that Europa's distance from Jupiter varies by about 6,000 kilometers over each orbital period, and the tidal force correspondingly varies in strength. This variation continuously flexes Europa's interior, and that flexing generates heat. The power produced by Europa's tidal heating is estimated at between 2 and 20 terawatts, a range reflecting the substantial uncertainty in the ice shell's viscosity and other material properties. Earth's entire geothermal heat flux, the heat flowing from Earth's interior to the surface, is approximately 47 terawatts. Europa's tidal heat source is comparable in total power to the natural geothermal heat flow of a planet 5 times its mass. This heat is distributed throughout Europa's interior, but concentrates at certain depths where the rate of deformation is highest. In the ice shell, tidal heating is most intense near the base of the shell, where the ice is warmest and most deformable. In the rocky interior, it concentrates near the boundaries of geological structures. The heat eventually conducts upward through the ice shell to the surface, where it is radiated into space. The implication for habitability is direct. The tidal heat keeps the ocean liquid. Without it, Europa's ocean would freeze. The orbit of Io, which drives the resonance, and the resulting eccentricity of Europa's orbit, is the physical reason that the ocean has existed for 4 billion years. This same mechanism operates to varying degrees at other moons in the outer solar system. Enceladus at Saturn, which has confirmed water plumes erupting from its south pole, is the most dramatic other example. Its tidal heating is intense enough to maintain a liquid ocean and drive active geysers. Titan at Saturn, Ganymede and Callisto at Jupiter, and potentially Triton at Neptune all show signs of internal heat that may be partly tidal in origin. The physical principle generalizes beyond the solar system. Any moon orbiting close to a sufficiently massive planet in an eccentric orbit will experience tidal heating. The conditions for tidal heating: massive planet, close orbit, maintained orbital eccentricity, are common in planetary systems throughout the galaxy. Europa-like moons, with tidal heating maintaining liquid water beneath an ice shell, may be among the most common habitable environments in the universe. Europa's ice shell sits between the vacuum of space and the ocean below, and it is one of the most studied geological objects in planetary science, despite the fact that no mission has ever directly sampled it. The thickness of the ice shell is one of the most contested questions in Europa science. The two leading models produce dramatically different pictures of how the ice shell works and what it implies about the accessibility of the ocean. The thin ice shell model proposes that the shell is only a few kilometers thick in some regions, perhaps as thin as 1 to 3 kilometers, in areas where warm ice from below has recently reached the surface. Under this model, the chaos terrain is produced by episodes where the ice shell nearly fully melted and ocean water directly interacted with the surface. Tidal heating in a thin shell is concentrated near the ice-ocean boundary, and warm ice or liquid water can reach the surface relatively easily. A thin shell is more accessible to a lander. Drilling a few kilometers is dramatically more feasible than drilling 50. The thick ice shell model proposes that the shell is 20 to 40 kilometers thick everywhere, with a cold, rigid upper layer sitting on a warmer, more ductile lower layer. Under this model, the chaos terrain is produced by convective overturned within the ice, warm ice rising as diapirs, blob-like upwellings, and cold ice sinking. without the shell ever fully melting or ocean water reaching the surface. The warm diapirs may melt through the upper rigid layer in some cases, producing the chaos terrain, but the ocean itself remains sealed and inaccessible. The observational evidence supports elements of both models. Surface features consistent with thin ice processes exist alongside features better explained by thick ice convection. It is possible that the shell thickness varies across Europa's surface, thinner in geologically active regions, thicker in older, quieter terrain. The shell may also vary in thickness over time as Europa's orbital eccentricity changes. The distinction matters enormously for mission design. A mission planning to access the ocean through the ice must know whether it is drilling through 3 kilometers or 50 kilometers. The engineering challenge scales roughly as the cube of the drilling depth. A 50-kilometer drill is not 10 times harder than a 5-kilometer drill. It is many orders of magnitude harder. The energy required to melt through 50 kilometers of ice is enormous. The communication systems required to send data up through 50 kilometers of ice are technically daunting. The time required to complete the drilling, perhaps decades for a simple melt probe, raises questions about spacecraft lifetime that have no easy answers. Europa Clipper's observations, particularly its ice-penetrating radar instrument REASON, which sends radio waves into the ice and detects echoes from internal boundaries, will help constrain the shell thickness. The radar cannot image the full depth of the shell with certainty, but it can detect the shallowest water-bearing features within the shell and characterize the upper portions of the ice structure. Combined with gravity measurements, magnetic field data, and the detailed surface imaging from mass specs and the cameras, the mission should substantially narrow the uncertainty in ice shell thickness. The answer matters not just for drilling missions. It matters for whether Europa's plumes, if they exist, carry ocean material to the surface. A thin shell, where material exchanges regularly between ocean and surface, means the plumes would be more oceanically representative. A thick shell where the ocean is sealed would mean plume material, if it exists at all, might come from isolated pockets of liquid within the ice rather than the main ocean. This distinction determines how much a plume sample tells you about ocean chemistry. If there is life in Europa's ocean, it is the most important discovery in human history. And if we contaminate Europa with Earth life before we discover it, we may never know whether what we find is theirs or ours. Planetary protection is the discipline concerned with preventing the contamination of solar system bodies with Earth life and preventing the contamination of Earth with extraterrestrial life. It has been a formal part of space mission planning since the early days of the space program, when Carl Sagan and others recognized that sending spacecraft to other worlds required thinking about the consequences of inadvertently carrying microbes along. Earth is not a sterile place, and neither are spacecraft. The interior of a spacecraft's cleanroom during assembly may contain fewer than a few hundred bacterial spores per square meter. But Earth's most robust microorganisms, the extremophiles, particularly spore-forming bacteria of the genus Bacillus, can survive the cleanroom environment, survive the vacuum of space for years, survive radiation doses that would kill most life, and potentially survive the journey to another world. For a mission to Europa, the planetary protection requirements are the most stringent ever applied to any planetary mission. Europa is classified as a Category 4 target, a destination where life is considered potentially possible. Spacecraft intended to land on Europa or penetrate its ice shell must be assembled in conditions of extraordinary cleanliness and sterilized using heat, chemical treatment, or radiation to reduce the bioburden to near zero. The specific challenge is that the very features of Europa that make it potentially habitable, the liquid water, the chemical gradients, the 4 billion years of stability, also mean that any Earth microbe that survived the journey and reached the ocean could potentially survive and reproduce in that environment. If a lander or cryobot inadvertently introduces even a single viable Earth microorganism to Europa's ocean, the possibility of false positives in subsequent life detection is real. The scientific community has not resolved the tension between the urgency of searching for life at Europa and the risk of contaminating the search before it begins. The compromise currently in place is to require sterilization standards for any mission that penetrates the ice and potentially reaches the ocean, while accepting somewhat lower standards for missions that remain above the ice and would not be in contact with any liquid water. The contamination problem has a personal scale that gets lost in the technical discussion. Consider the people who would build a Europa lander or cryobot. They would work for years in clean rooms, wearing bunny suits that cover everything, including their faces, breathing filtered air, handling spacecraft components with gloved hands, following procedures designed to minimize the chance of shedding a single skin cell that could harbor a viable microorganism. And they would know that the mission they're building is designed to go somewhere life might exist, and ask whether life exists there. That is a specific kind of responsibility that very few humans have ever faced. It is the engineering equivalent of choosing every word carefully, because a misstatement could change the course of history. Not metaphorically. Actually, Europa Clipper entered the Jovian system in April 2030. Let's be specific about what that means in engineering terms, because the architecture of the mission is itself a lesson in how to solve the radiation problem that every Europa mission must solve. The spacecraft is the largest planetary science mission NASA has ever launched. Its solar arrays span over 30 meters. Tip to tip, wider than a 10-story building is tall. Because at Jupiter's distance from the Sun, sunlight delivers only about 4% of the energy it delivers at Earth's orbit. And the spacecraft's instruments and communication systems require substantial power. The body of the spacecraft itself is densely packaged. 9 science instruments, a radiation-hardened vault protecting the electronics, and propellant tanks constituting the majority of the spacecraft's dry mass. The vault is worth dwelling on. It is a metal box, aluminum and tantalum, enclosing the most sensitive electronic components of the spacecraft. The vault walls are thick enough to reduce the radiation dose inside to approximately the same level as the ambient radiation environment at Earth's surface. Outside the vault, the radiation environment at Europa's orbit would destroy unprotected electronics within hours. Inside the vault, those same electronics can operate normally. The trade-off is mass. The vault adds hundreds of kilograms to the spacecraft. That mass has to be launched from Earth and carried to Jupiter, which costs propellant. But the alternative, allowing radiation to damage the electronics, is not acceptable. The vault is a necessary tax on the mission's mass budget, paid in exchange for the ability to operate in Europa's environment. The mission architecture avoids Europa's radiation belt as much as possible, rather than orbiting Europa directly, which would keep the spacecraft inside the most intense part of Jupiter's radiation environment continuously. Europa Clipper orbits Jupiter on a path that brings it close to Europa for brief flybys, then carries it away from the intense radiation zone during the long arcs of its orbit. During a typical flyby, the spacecraft spends only a few hours within the dangerous inner radiation zone. It then spends days or weeks on the outer portions of its orbit, where the radiation flux is orders of magnitude lower, transmitting data to Earth and allowing its onboard systems to recover. This approach limits the total accumulated radiation dose by reducing the time spent in the worst environment. Over the projected 49 flybys of the extended mission, Europa Clipper will accumulate approximately 2.9 million rad of total ionizing dose, within the design tolerance of its radiation-hardened components, but not with large margins. The scientific instruments are each designed with this harsh environment in mind. Reason: the radar for Europa assessment and sounding. Ocean to near surface is an ice-penetrating radar that sends radio waves into Europa's surface and detects echoes from subsurface boundaries. Its ability to see beneath the ice depends on the wavelength of the radar waves and the properties of the ice. And it is designed to probe features within the upper portions of the ice shell and potentially detect water pockets or the base of the ice if it is shallow enough in some regions. MASSPEX, the M-AS spectrometer for planetary exploration, is designed to analyze the chemical composition of Europa's tenuous atmosphere and any plumes encountered during flybys. It can detect individual molecules and measure their masses with sufficient precision to identify complex organic compounds if present. If Europa has active water plumes carrying ocean material to space, MASSPEX is the instrument that would detect the chemical signature of that ocean material during a flyby. ETHEMIS, the Europa Thermal Emission Imaging System, maps the thermal emission from Europa's surface, identifying regions that are anomalously warm compared to their surroundings. Warm spots on the surface could indicate geologically active regions where heat from below is reaching the surface, the same regions that might have thin ice, active plumes, or recent cryovolcanic deposits. The thermal map from ETHEMIS will guide the selection of landing sites for any future lander mission. The EIS camera, Europa Imaging System, is the mission's visual camera, designed to image Europa's surface at resolutions approaching the meter scale during the closest flybys. The images from EIS will provide the detailed surface maps that mission planners need to understand the diversity of Europa's terrain and identify the scientifically highest value, engineering safest locations for a future landing. Each instrument tells part of the story. No single instrument can answer the life question. Together, they are building the dataset that will guide the next 30 years of Europa exploration. No space agency is currently planning to send humans to Europa. The engineering challenges are sufficiently severe, the robotic alternatives sufficiently capable, and the resource requirements sufficiently enormous that a crewed Europa mission is, at the current state of human spaceflight, a topic for mission architecture studies rather than program planning. But the question of what a crewed mission would look like, what it would require, what it would cost in human terms, what it would mean for the people who went, is worth examining carefully, because it reveals things about the Europa environment that robotic mission summaries tend to gloss over. The radiation is the first and most important constraint. We established the dose rate, approximately 5,400 rem per day at Europa's orbital distance. An unprotected human would receive a lethal dose in roughly 2 hours, even with the best shielding available to current technology. A human crew spending extended time in the inner Jovian system would accumulate radiation doses that would substantially elevate their lifetime cancer risk and potentially cause acute radiation sickness, depending on the specific trajectory and time spent in the most intense regions. Current spacecraft radiation shielding for crewed missions uses polyethylene, a hydrogen-rich polymer that is effective at stopping secondary neutrons, combined with structural aluminum. A shielded crew habitat providing the equivalent of a few grams per square centimeter of polyethylene shielding, would reduce the dose rate at Europa to perhaps 50 to 100 rem per day. Still 10 to 20 times the daily dose that would be considered the upper acceptable limit for prolonged occupational exposure on Earth, but survivable for the duration of a short stay. The specific crewed mission architecture that most engineering studies envision involves a rapid transit to Europa, using nuclear propulsion to minimize transit time, thereby minimizing the dose accumulated en route, followed by a brief operational period at Europa of days to perhaps a few weeks, followed by a rapid return transit. The shielding on the crewed habitat would be concentrated in the sleeping and living areas, where the crew spends the most time, while operational areas where the crew works during flybys accept higher doses. The crew members on such a mission would know, before they launched, that they were accepting a radiation dose that would measurably increase their lifetime risk of cancer and potentially cause other health consequences. They would accept this knowingly, in the same way that test pilots accepted the risks of experimental aircraft or Antarctic explorers accepted the risks of their expeditions, not ignorant of the danger. But judging that the goal was worth it, the psychological dimension of the radiation risk is specific and interesting. Unlike the radiation risks of cancer that develop over years after exposure, some forms of radiation damage to the central nervous system from high-energy heavy ions, can cause cognitive effects detectable within weeks to months of high-dose exposure. Astronauts on Mars missions face this concern, and Europa missions face it more acutely. The crew would be performing complex scientific and engineering operations while potentially experiencing the early effects of central nervous system radiation exposure. Mission planning would need to account for the possibility of degraded cognitive performance. Beyond radiation, the crewed mission faces the same long-duration spaceflight challenges described for the Alpha Centauri journey: bone loss, muscle atrophy, immune suppression, fluid shifts, but on the somewhat shorter timeline of a Jupiter mission. The 6-year round trip allows time for serious physiological deterioration. Countermeasures developed for ISS missions, exercise regimens, pharmacological interventions, nutritional strategies would be applied, but their effectiveness over 6-year timescales is uncertain. ISS experience spans up to a year of continuous spaceflight, and a handful of cases approaching 2 years. 6 years is beyond the data we have. The communication delay is also a psychological and operational factor on a different scale from any previous crewed mission. At Earth ISS distances, communication is essentially instantaneous. At Mars distances, the round-trip delay reaches up to 44 minutes at maximum, manageable for most operational scenarios, though not for true emergencies. At Jupiter distances, the round-trip delay reaches over 100 minutes. A crew at Europa experiencing a medical emergency or a system failure would have to diagnose and address the problem entirely on their own for nearly 2 hours before ground support could even receive their distress call. Ground support's response would arrive another hour after that. This communication delay means the crewed Europa mission, more than any previous human spaceflight, requires a crew that is genuinely self-sufficient. Not self-sufficient in the way ISS crews are self-sufficient, with ground support monitoring every system in real time, and astronauts who primarily execute procedures developed on the ground, but truly self-sufficient in the way of historical polar expeditions or transoceanic voyages. A team that must solve problems with the resources on hand, without timely external guidance, relying on training, judgment, and each other. Crew selection for a Europa mission would require not just technical expertise and physical fitness and psychological resilience, but a specific kind of deep competence. People who understand their systems well enough to innovate under pressure, who have practiced enough scenarios to handle the genuinely unexpected, who have the interpersonal skills to maintain team function under extreme stress over years of isolation. This is a demanding selection filter, and the pool of people who meet all these criteria is small. Who would volunteer? The history of exploration suggests that volunteers would not be in short supply. The first crewed Mars missions will face comparable challenges, and the planning process for those has already revealed an enormous pool of people interested in accepting the risks. The specific draw of Europa, the possibility of participating in the search for life in an ocean that might be inhabited, is an unusually powerful motivator. The person who discovers life beyond Earth will have done something that changes human self-understanding more profoundly than any individual act in recorded history. The probability that a single crewed Europa mission achieves that specific discovery is not high, but the possibility is real, and for certain kinds of people, the possibility is enough. Let's go beneath the ice, past the 50 kilometers of frozen water, past the gradual transition from cold, brittle ice at the surface to warm, ductile ice at the base of the shell, through the base of the ice shell and into the water below. Europa's ocean is dark, not dark in the way a cloudy night is dark. Dark in the absolute sense that no photon from the sun has reached this water for the entire history of the solar system. The ice above absorbs and scatters what little sunlight reaches Europa's surface. At the depth of the ocean, darkness is total and permanent. The water is cold near the ice-ocean interface, perhaps just above the freezing point of the ammonia salt solution that makes up the ocean at that boundary. It warms slightly with depth because the heat source is below from the rocky seafloor, and the ocean circulates to distribute that heat upward. The temperature gradient is shallow, not the dramatic temperature contrast between deep cold water and shallow warm water that characterizes Earth's ocean thermoclines, but present. The salinity of the ocean is uncertain. Spectroscopic measurements of Europa's surface have detected magnesium sulfate, sodium chloride, and other salts, the products of ocean water reaching the surface and being processed by radiation. These surface measurements indicate that the ocean has been in contact with the seafloor rock and has dissolved minerals from it. But the exact concentrations are not well constrained. The ocean could range from somewhat less salty than Earth's ocean to several times saltier. And the specific salt composition affects everything from the ocean's thermal properties to the chemistry available for life. The seafloor is where the most interesting processes may be occurring. Water, interacting with warm basaltic rock, undergoes serpentinization, a hydrothermal process in which water reacts with iron-magnesium silicate minerals, producing serpentine minerals, magnetite, and hydrogen gas. This process is exothermic. It releases heat. It operates at temperatures well below the boiling point of water. It requires no sunlight. It produces hydrogen, which is an energy source for chemosynthetic organisms. On Earth, serpentinization occurs at sites called low-temperature hydrothermal systems, including the Lost City hydrothermal field discovered in 2000 at the Mid-Atlantic Ridge, which produces hydrogen and methane from the interaction of seawater with mantle rock. The Lost City field hosts a rich microbial community, despite being far from the energy-rich black smoke events that were the first hydrothermal ecosystems discovered. Europa's seafloor may be covered with environments similar to the Lost City. not high-temperature black smoke events driven by volcanic heat, but lower-temperature serpentinization systems driven by tidal heat conducting through the rock. The tidal heating that keeps the ocean liquid is not uniform. It concentrates in specific regions depending on the distribution of material properties in the interior. And these concentrations might produce regional hotspots on the seafloor, analogous to volcanic systems but driven by tidal flexing rather than magma. Whether these hotspots are sufficient to drive the kind of hydrothermal circulation that supports Earth's deepest ecosystems is unknown. The energy flux at Europa's seafloor is estimated to be lower than at Earth's mid-ocean ridges, where black smokers form. But the total power available, several terawatts, is not negligible, and it has been available continuously for 4 billion years. 4 billion years. The same 4 billion years during which Earth's life evolved from chemistry to bacteria to complex multicellular organisms. To us, if the seafloor chemistry at Europa has been operating continuously for that duration, and if that chemistry can provide the energy gradients that life exploits, then the question is not whether there has been enough time for life to start, but whether the conditions have been consistent enough for life to persist once started. Persistence is the key word. Life on Earth has survived 5 major mass extinctions: asteroid impacts, snowball Earth glaciations, dramatic changes in atmospheric composition, and the gradual brightening of the sun over geological time. Each of these events challenged the biosphere severely and eliminated enormous fractions of the species present at the time. But life itself persisted through every extinction. The adaptability of life, the speed at which it evolves new strategies in response to changing conditions, means that as long as some energy sources and liquid water remained accessible, life found a way to continue. Europa's ocean has had fewer of these destabilizing events than Earth has. The tidal heating is steady, varying on the timescale of orbital evolution, rather than catastrophic events. The ice shell insulates the ocean from the radiation above. The rock below provides the mineral chemistry that life needs. If life started in Europa's ocean, the conditions for its continuation have been remarkably stable for 4 billion years. Europa Clipper's most direct evidence for the subsurface ocean will come from its magnetometer, building on the Galileo measurements that established the ocean hypothesis. The physics of induction, the generation of electrical currents in a conductor by a changing magnetic field, is well understood, and its application to Europa is elegant. Jupiter's rotating magnetic field sweeps past Europa every 10 hours, presenting Europa with a changing external magnetic field. Any electrically conductive material inside Europa will respond to this changing field by developing induced electrical currents. And those currents generate their own secondary magnetic field that can be detected by a magnetometer on a passing spacecraft. The amplitude and phase of the induced magnetic field carry information about the conductivity and geometry of the conducting layer. A thin, highly conductive layer close to the surface produces a different inductive signature than a thick, moderately conductive layer at depth. By measuring the inductive response at multiple frequencies, which requires observing Europa at multiple times during the Jovian rotation period, Europa Clipper can constrain the depth and conductivity of the conducting layer. The planned measurements by Europa Clipper's ICIMAG magnetometer during the 49 planned flybys will sample Europa at many different orbital phases of Jupiter's rotation, providing a dataset many times richer than Galileo's more limited observations. The result should be the most precise determination yet of the ocean's depth below the ice surface, directly addressing the thin versus thick ice shell debate, and of the ocean's salinity, which the conductivity measurement constrains. There is also a subtler measurement possible: the detection of non-inductive magnetic perturbations that would indicate the existence of convective currents within the ocean itself. If Europa's ocean has sufficiently strong convection, driven by thermal gradients between the cold ice above and the warmer seafloor below, the moving conductive fluid would generate magnetic field variations on top of the inductive signal. This kind of ocean circulation is analogous to the dynamo process that generates Earth's magnetic field, but at much smaller scales. Detecting it would require extracting a small signal from a background dominated by the much stronger inductive response. But it is within the sensitivity limits of IceMag if the convection is vigorous enough. Convection in the ocean has direct implications for the prospects for life. Convective circulation distributes heat and chemical species throughout the ocean. It carries nutrients from the seafloor upward toward the ice-ocean interface. It mixes the ocean and prevents stratification that would concentrate life-supporting chemistry in narrow zones near the seafloor. Strong convection means a well-mixed ocean where chemical gradients drive biological activity throughout the water column, rather than only at specific interfaces. The inductive measurements will not tell us whether life exists in Europa's ocean, but they will tell us what kind of ocean it is, its depth, its conductivity, its likely circulation regime. And this information directly constrains what kind of life would be possible there. If material from Europa's ocean reaches the surface, through plumes, through cryovolcanism, through the slow cycling of ice that brings ocean-contaminated ice from the base of the shell to the surface over geological time, then the surface chemistry of Europa is a partial record of the ocean chemistry below. This is the logic behind the surface spectroscopy instruments on Europa Clipper. MEIS, the Mapping Imaging Spectrometer for Europa, measures the infrared spectrum of surface materials across the full disk of Europa and in detail during close flybys, producing a map of surface composition that will reveal the spatial distribution of different chemical species. The infrared spectrum of a material is its molecular fingerprint. Each type of molecule absorbs infrared light at specific wavelengths determined by the vibrational modes of its chemical bonds. Water ice absorbs at characteristic wavelengths. Sulfate salts absorb at different wavelengths. Organic compounds absorb at still other wavelengths. By measuring the infrared spectrum of Europa's surface, MEIS can identify what chemical species are present in each region. The brown and reddish material that colors the chaos terrain and the ridge systems of Europa is one of the primary targets. This material has been analyzed in earlier observations and found to contain sulfate minerals, consistent with ocean water that has evaporated or been processed by radiation. But the specific mixture of compounds in the reddish material is not fully characterized. It may contain organic compounds produced by the radiation processing of ocean-derived organics. It may contain biologically produced compounds, if life exists in the ocean. The detection of specific amino acids, the building blocks of proteins, in the surface material would be extraordinarily significant. Amino acids are produced by abiotic chemistry, so their presence alone would not prove life. But the specific mixture of amino acids present could distinguish between abiotic and biological origins. Abiotic processes produce amino acids in approximately equal amounts of left-handed and right-handed forms, the two mirror image configurations that exist for most amino acids. Life, on Earth at least, uses almost exclusively left-handed amino acids. If a sample of Europa's surface material showed a strong preference for one-handedness, an excess of left-handed or right-handed amino acids, compared to the equal mixture expected from abiotic chemistry, it would be a powerful biosignature. Europa Clipper cannot measure amino acid handedness from orbit. That requires laboratory analysis of a physical sample. But the mass spectrometer AMOSPEX can detect the molecular masses of complex organic compounds in plume material, and the identification of specific molecular species that are difficult to produce abiotically would be a strong indicator of ocean chemistry, worthy of further investigation. The full power of surface chemistry analysis will only be available when a lander physically collects and analyzes a sample. But the orbital observations provide the context for interpreting what a lander should look for and where the highest priority sampling sites are. Let me walk you through what Europa Clipper is actually doing as it orbits Jupiter, because the specific sequence of flybys is itself a kind of story about how we approach a place that wants to kill our machines. After Jupiter orbit insertion in April 2030, Europa Clipper settled into a large elliptical orbit around Jupiter, with a period of roughly 2 weeks. This orbit carries the spacecraft from Apogee, farthest distance from Jupiter, safely outside the most intense radiation zones, down to Perigove, closest approach to Jupiter, and back. The orbital geometry is designed so that each Perigove approach can be timed to coincide with a close approach to one of the Galilean moons. The early flybys in the mission are not all of Europa. Ganymede and Callisto, the outer 2 Galilean moons, are visited first, partly for their own scientific value and partly because these flybys are used to shape Europa Clipper's orbit gravitationally. By timing the flybys precisely, the spacecraft uses the moon's gravity to change the shape and orientation of its orbit around Jupiter, migrating it progressively inward toward Europa's orbit, without burning propellant. This technique, resonance orbit mechanics, is the same principle as using planetary gravity assists during interplanetary travel, applied here to navigate within a planetary system. As the orbit migrates inward, the radiation environment intensifies. Each Europa flyby takes the spacecraft deeper into the heart of Jupiter's radiation belts. The instrument operations team carefully plans which instruments are active during which portions of each flyby, managing the accumulated dose to each instrument against the science data needed. Some instruments are turned off during the highest radiation portions of a flyby to preserve their functional lifetime for the full mission. The closest Europa flybys, those within 25 kilometers of the surface, are the most scientifically productive and the most radiation intense. During these approaches, the spacecraft's cameras can image the surface at meter-scale resolution. MASPEX can detect the faintest traces of plume material, if any exists. The magnetometer measures the local magnetic environment with the highest precision achievable from orbit. But the spacecraft is also receiving the highest radiation dose during these closest approaches. The mission managers monitor the accumulated total ionizing dose against the spacecraft's design tolerance, managing the flyby sequence to stay within safe limits. If the radiation environment is harsher than predicted, if Jupiter's radiation belts have fluctuated from their baseline state in ways the models did not anticipate, the mission might need to be modified, reducing the number of closest flybys or changing their orbital geometry to reduce exposure. This is the operational reality of exploring in the Jovian system. Every decision involves a trade-off between science return and hardware lifetime, with radiation exposure as the currency of that trade-off. It is management of a consumable that cannot be replenished. the spacecraft's tolerance for radiation is finite. The environment is unforgiving, and the mission must be conducted within those constraints. There is a 50-year arc to the Europa story, and it is worth tracing because it reveals something about how science progresses toward the most important answers. The Voyager flybys in 1979 were the first close look at the Galilean moons. Voyager 1 passed within 733,000 kilometers of Europa, and Voyager 2 within 206,000 kilometers. The images were revolutionary. They showed a surface without the large craters expected for an ancient, geologically dead moon, covered instead with a complex network of brown, linear features crossing the ice. The immediate impression was of a cracked eggshell. Whatever was inside had been pushing on the surface from below. The Galileo mission from 1995 to 2003 transformed that impression into a scientific hypothesis. The magnetic field measurements established the ocean. The high-resolution images of chaos terrain and ridges established the geological activity. The near-infrared spectra established that salts were present on the surface, likely derived from below. By the time Galileo's mission ended, the spacecraft deliberately crashed into Jupiter to prevent any possibility of it later crashing into Europa and contaminating it. The ocean was accepted. The ocean was real. The next question was what was in it. The next 2 decades produced proposals for Europa missions that did not get funded. Budget constraints, competing mission priorities, technical challenges too severe to resolve within available resources. The scientific community watched other targets. Mars, Titan, Enceladus receive missions while Europa waited. The argument for Europa's importance never weakened. The arguments about cost and risk kept it from the top of the priority list. Europa Clipper was approved, funded, and built across the 2010s and 2020s, a 13-year development process involving thousands of scientists and engineers. Its launch in 2024 and arrival in 2030 represented the culmination of 50 years of scientific effort since Voyager's first glimpse of the cracked ice. The next phase, a lander, a cryobot, access to the ocean, represents another generation's work. The mission concepts exist. The scientific rationale is unambiguous. The technology is being developed, component by component, in laboratory experiments and engineering demonstrations. The physical hardware that will eventually reach Europa's ocean is being designed by people who were not yet born when Galileo visited the moon. This is how the most important scientific questions get answered, not in a single leap, but in a sequence of steps across generations, each step building on the last. The target coming into focus gradually as technology and understanding advance together. The ocean that Voyager glimpsed in 1979 as an inference from a cracked surface, that Galileo confirmed through magnetic measurements in the 1990s, that Europa Clipper will characterize from orbit in the 2030s, will eventually be accessed directly by hardware that does not yet exist, operated by scientists who are currently in primary school. The 50-year arc has not ended. It has reached its middle chapter. It is worth being precise about why Europa receives more attention and investment than Enceladus, because Enceladus has confirmed plumes, a confirmed subsurface ocean, confirmed hydrothermal activity, and confirmed complex organic chemistry, all of which Europa has not yet confirmed definitively. The answer is partly about history and partly about size. Enceladus's plumes were discovered in 2005 by the Cassini spacecraft. They have been observed continuously since then. The scientific case for habitability at Enceladus is strong precisely because the plumes have allowed direct sampling of ocean material. Cassini's mass spectrometer detected molecular hydrogen, indicating active hydrothermal chemistry. Detected complex organic molecules, including compounds with masses above 200 atomic mass units, suggesting biological or pre-biological complexity, and detected silica nanoparticles, indicating water temperatures above 90 degrees Celsius at the seafloor. By every measure of detectable evidence, Enceladus is more obviously and dramatically promising for life than Europa. And yet the community's focus has historically been on Europa. The reason is ocean volume. Enceladus is a small moon, 504 kilometers in diameter, roughly 1/7 the diameter of Europa. Its subsurface ocean is also small, a regional sea beneath the South Polar region, perhaps a global ocean beneath an ice shell, but in either case containing far less total water than Europa's global ocean. Europa's ocean, with its 3 times Earth ocean volume, represents an environment orders of magnitude larger in total extent. Ocean volume matters for life because it affects the probability of life having arisen in the first place, and the diversity of ecological niches available if it did. A larger ocean has more total chemistry occurring, more total material cycling, more opportunity for the rare events that may be required for the origin of life. An ocean the size of Europa's, if it supports life at all, would likely support more total biomass and more ecological diversity than the smaller Enceladus Sea. There is also the question of geological time. Enceladus is geologically young in its active South Polar region. The extreme activity there may be episodic, driven by current tidal conditions that may not have persisted for the full history of the solar system. Europa's ocean has almost certainly been continuous for billions of years. The longer continuous duration of habitability increases the probability of life having had time to arise and persist. This is not to diminish Enceladus. A confirmed biochemical detection at Enceladus would be as world-changing as one at Europa, and the easier physical access through confirmed plumes makes it in some ways a more tractable target for near-term life detection. Future missions to the Enceladus Ocean are under active study, and the scientific community increasingly sees Europa and Enceladus as complementary targets rather than competitors. But Europa came first in the attention of the scientific community, and Europa represents the possibility of the larger ocean, the ocean more likely to have had the conditions for life's origin sustained for billions of years. That is why a flagship-class mission was built for Europa, and why the arc of missions leading toward Europa's ocean will continue even as Enceladus receives its own eventually. There is a dimension of the Europa discovery question that scientific discussions tend to set aside. What happens on Earth the day after a confirmed detection of life in Europa's ocean? Not the science that follows. That is well understood. A cascade of follow-up missions and analyses that would occupy the scientific community for decades. The human dimension. The cultural, philosophical, religious, and political responses to learning that life exists somewhere other than Earth. The scientific community has been grappling with this question in advance. The SETI protocols, Search for Extraterrestrial Intelligence, have established procedures for what to do after a detection of intelligence beyond Earth. Astrobiologists have begun similar discussions for how to handle a confirmed detection of microbial life at Europa or Enceladus. The International Council of Scientific Unions has established working groups. NASA has internal protocols. There are official processes in place, however imperfect, for managing a discovery that would be the most significant announcement in human history. But official processes cannot predict or fully manage the cultural response. Consider what it would mean for religious traditions that place humanity at the center of creation, or regard Earth as uniquely privileged among all worlds. Consider what it would mean for philosophical traditions that derive human dignity from the rarity or uniqueness of consciousness. Consider what it would mean for people who have organized significant portions of their worldview around the assumption that we are alone. The discovery would not destroy any of these frameworks. Religious and philosophical traditions have absorbed transformative scientific findings before, from heliocentrism to evolution to the Big Bang, and have found ways to integrate them with their core commitments. But the integration takes time and involves genuine struggle, and the announcement of life at Europa would arrive faster than that integration could occur for most people. The scientists who make the discovery would face immediate pressure to confirm the finding through multiple independent analyses before announcing, to communicate the result clearly and honestly without overstatement or understatement, to provide context for what the discovery means and does not mean, and to navigate the public response while continuing to do science. The discovery itself would almost certainly not arrive as a single dramatic announcement. It would more likely be a series of progressive findings. First, chemical compounds in plume material that are consistent with biological origin, but not definitive. Then additional analyses that narrow the alternatives. Then a formal paper asserting that the biological interpretation is the most parsimonious explanation of all available data. Then the scientific community's response. Challenges, alternative interpretations, follow-up experiments. Then, gradually, consensus. The most careful scientists in the relevant fields agree that the evidence is most consistent with life. This is how the discovery of life beyond Earth will probably happen. Not as a single revelation, but as a slowly building scientific consensus. And that gradual process will give the world some time, however limited, to prepare for the final answer. We have discussed the radiation, the ice, the ocean, the chemistry, the mission architecture, the engineering challenges, the philosophical implications. Let me name the thing that sits underneath all of it, and that makes Europa different from every other destination we have explored, or plan to explore. Every other target in human space exploration is interesting because of what it might reveal about physics, about geology, about the history of the solar system, about the limits of what our technology can achieve. These are important reasons. They are the reasons we have sent probes to Mercury and Venus and Mars and Saturn and Pluto and the comets. Europa is interesting because of what might be alive there, not what might have lived there once. The traces of ancient biology that Mars scientists search for in billion-year-old sedimentary rock. Not what chemical precursors to life might exist there. The complex organic chemistry that makes Titan fascinating. Alive, present tense, right now. In the ocean below the ice. If life exists in Europa's ocean, it is alive tonight. As you read these words, organisms in Europa's dark ocean are metabolizing, reproducing, responding to their chemical environment, processing chemical energy in ways that distinguish them fundamentally from the non-living chemistry around them. They have been alive for billions of years. They have been alive through every event in Earth's history. Through the extinction of the dinosaurs, through the emergence of the first animals, through the formation of the oldest rocks, through billions of years of biological evolution that produced everything alive on Earth today. They have been alive in the dark, under the ice, without ever knowing that somewhere in the same solar system, on a planet warmed by the same sun, chemistry also became biology. And that biology eventually became something that built a spacecraft and sent it toward their ocean to ask whether they were there. That is what Europa is. That is what the journey is for. Not the physics, not the engineering. The question. The ice is 50 kilometers thick. The ocean is 3 times the volume of Earth's oceans. The radiation at Europa's orbit would kill an unprotected person in 2 hours. The journey from Earth takes 6 years. The communication delay makes real-time control impossible. The contamination protocols require the highest standards of spacecraft sterilization ever applied. All of this is true. All of this constitutes a terrifying journey in the most literal sense of that word. A journey into an environment hostile to life and machines alike, toward a destination whose significance would be the most profound in human history, if the answer is what we hope it might be. But a spacecraft is already there. Its instruments are operating. Its cameras are imaging the ice. Its magnetometer is reading the ocean's signature in Jupiter's magnetic field. Its mass spectrometer is sampling the tenuous atmosphere for traces of what lies below. We are asking the question, right now, tonight. The ice holds its answer. The ocean below holds it in every organism, if any exist, in every molecule, in every chemical gradient that either is or is not the product of life. We will find out. That is the most important sentence in the history of human exploration. We will find out. Tell us in the comments where on this planet you're listening from tonight. Your city, your country, whatever corner of this world you're in right now, while these questions are being asked at a moon 485 million miles away. We want to know where you are. It matters. Drop it below. And if tonight gave you something to carry into the quiet before sleep, the weight of what might be in that ocean. The specific fact that we are right now in the process of finding out, like the video and subscribe to Calm Theory for sleep. We'll be here, watching the data come in. Sleep well.